the Honors Chemistry section 17.4 lesson video, but it's going to be part 1. This section's kind of long, so I'm going to break it up into 2 different parts. So remember, if you want all my videos in one place, just subscribe and you'll see them all there together. Alright, so we have 2 main types of problems we have to talk about in section 4, and that is Hess's Law and standard heat of formation problems. So let's jump into Hess's Law first. So Hess's Law's heat summation states that if you add 2 or more thermochemical equations to give a final equation, then you can also add the heat changes to give the final heat change. So if you add reactions together, you can add their delta H's in order to make a final delta H for your new equation. Now, there are a couple of things that you can do when you add reactions. So the first thing is you can leave the reaction the same. So we'll put reaction stays the same. If the reaction stays the same, then the delta H also stays the same. You can flip a reaction. And by that, I mean we take our reactants. So say it's A plus B yields AB. If we flip a reaction, that means we put our products as reactants and our reactants as products. So if you flip a reaction, you change the sign for delta H. So like let's say...
Ms. Waters.
Yes?
Pardon the interruption. Do you have Siobhan?
No ma'am, it's my planning period.
Oh, okay, thank you.
You're welcome. Well, sorry about that. I do these during my planning period, so that kind of stuff doesn't happen. So my kilojoules is 50. So then if I flip the reaction, we would say, okay, well now it's negative 50 kilojoules like that. That's what you do when you flip a reaction. And then the last thing you can do is you can multiply or divide a reaction by a number. And if you do that, you multiply or divide delta H by the same number. So let's say my reaction again is A plus B yields AB, but I need double that. So say I want to change it to 2A plus 2B yields 2AB. Well, my original delta H we said was 50 kilojoules. So if I multiply the reaction by 2, I'll just multiply delta H also by 2, and so it will become 100 kilojoules. Okay, so these are the options that we have. We can leave a reaction the same and delta H will remain the same. We can flip a reaction, so switch the products and reactants, and the sign of delta H will change. Or we can multiply or divide a reaction by a number, and when we do that, we multiply or divide delta H by that same number. So let's look at some together. I personally love doing Hess's Law problems because I think they're really fun. So we'll see what you think. So let's start out with something really, really easy. So it says calculate the enthalpy change for the following reaction given the following information. So the first thing you do is look at your 2 reactions. We're trying to add these to make this reaction. So I have some PBs, I have some Cl2s, I have a PbCl4 and a PbCl2. So the first thing is you need to determine what should you look at in each reaction. So what I always like to do is find something that doesn't happen in both reactions. So see how they both have Pb, they both have Cl2, but only this reaction has PbCl4 and only this reaction has PbCl2. I like to find those unique substances because then I can tell what am I supposed to do with them. Alright, so here I have 1 PbCl4 as a product. In my final reaction, I want 1 PbCl4 as a product. So this is an example where I'm not going to change the reaction. I'm going to leave it the same. So I'm just going to rewrite it. So Pb plus 2Cl2 yields PbCl4. Since I did not change the reaction, I am not going to change delta H. So it stays as negative 329.2 kilojoules. Okay, so again, the reason I did not change this reaction was PbCl4 was already on the correct side, the product side, and we had the correct amount. We have 1. Alright, so now let's look at PbCl2. Well, I have 1 PbCl2 as a product. I want 1 PbCl2 as a reactant. So this is an example of where I'm going to flip a reaction because see, I need it, see where the arrow is? I need it on the other side. So when you flip a reaction, you just write the products first. So PbCl2 yields Pb plus Cl2. When you flip a reaction, you change the sign of delta H. So see, it was negative, so I'm going to change it to positive. So it becomes 359.4 kilojoules. Now, the next step is we need to add up to make sure our reactions equal this reaction. So the way it works is, see how I lined up my arrows? You'll want to line your arrows up. Same substances that are shown on both sides of the arrow will cancel out. So see how we have a PB on the reactant side and a PB on the product side? Those cancel. We have two Cl2s, and here we have one Cl2, so that means one of the Cl2s will cancel. So I get rid of this one, and here I'll just mark out the 2. And then whatever you have left adds together. So I have a PbCl2, I have a Cl2, my arrow, and a PbCl4. So is that the reaction that we wanted? Yes. So once I get the reaction I want, I just add my delta H's. And so when I add my delta H's for these, I got 30.2 kilojoules. And so there's my answer. All right, so Hess's Law is just all about manipulating your reactions to make a new reaction so then you can add the delta H's. All right, so let's look at another one. All right, so if you feel confident, go ahead and pause it and try it, or if you just want to hang out and see another one real quick, that's fine too. All right, so here's the reaction we're trying to make. Here's the two reactions I have to look at. All right, so first let's pick what is unique about each reaction. So if you look, we have a PCl5, a PCl3, and a Cl2. Well, both of the reactions have PCl3, both of the reactions have Cl2. So that means in my first reaction, I'm going to look at PCl5. And then in my second reaction, I have a P, a Cl2, and a PCl3. So again, they both have PCl3, they both have Cl2. So I'm going to look at the 2P. All right, so I have one PCl5 as a reactant. I want two PCl5s as a product. So I'm going to have to do two things to this reaction. One, I'm going to have to flip it to get it on the product side, but I'm also somehow got to turn it into 2. So I'm going to multiply it by 2. Okay, so I'm going to flip and multiply it by 2. If I flip it, that changes the sign, so now this will be negative. If I multiply the reaction by 2, I also need to multiply delta H by 2. Alright, so let's see what that's going to look like. So when I flip it, that means I'm going to write the products first. So PCl3 plus Cl2 yields PCl5. But I didn't just need to flip it, I also need to multiply it by 2. So I just take all my coefficients, which happen to be 1s, and multiply them all by 2. So then delta H, like I said, becomes negative because we changed the sign, but we also have to multiply it by 2. And so when you do that, you get negative 175.8 kilojoules. All right, so we got our first reaction. See, now we have 2 PCl5 as a product, which is exactly what we want. All right, so our bottom one, we have 2P as a reactant. I want 2P as a reactant, so I don't have to do anything to this one. So I'm just going to rewrite it. So 2P plus 3Cl2 yields 2PCl3. If I don't change a reaction, then I don't change the delta H. So let's make sure we got the right reaction. So remember, things that are on opposite sides of the arrow will cancel. So like I have a 2PCl3, a 2PCl3. So those are going to cancel. That's the only thing that cancels. So I write what's left. Well, I have 2 P's. Now the Cl2s don't cancel because they're on the same side of the arrow. So I'm going to add them together. So 2 plus 3 is 5 Cl2 yields 2 PCl5. So is that the reaction that I want? Yes. And so then last step is add up those delta H's. See, it's kind of like a game. You know, I mean, I think it's like a game. You may or may not agree with me, but that's fine. So I got negative 749.8 kilojoules. Alright, and so that's Hess's Law. Like I said, we're just manipulating reactions to make a final reaction. So let's look at another one. Alright, so if you haven't tried one on your own, pause this one, go ahead and try it, and then check back with me. So let's look at this one. Alright, so first I'm going to figure out what I'm looking at. So they both have NH3, they both have O2, they both have H2O. So I'm going to look at the N2 and the NO. Alright, so I have 2 N2 as a product. I want 1 N2 as a reactant. So clearly I'm going to have to flip it to get it on the correct side. Now I have 2 and I only want 1. You can't subtract or add, you can only multiply or divide. So I'm going to divide this reaction by 2. Okay, so if I flip it, I change the sign, so my negative is going to become positive. If I divide the reaction by 2, I'm also going to divide delta H by 2. Alright, so let's look at what that's going to look like. So I'm going to flip it by writing the products first, but I'm also going to divide by 2. So 2 N2 is just going to become N2. 6 H2O is going to become 3 H2O. 4 NH3 is going to become 2 NH3. And then 3 O2 is going to become 3 halves, or I'll change it to a decimal, 1.5 O2. Alright, so we flipped and divided our first reaction by 2. Alright, so let's look at our second reaction. So we have 4 NOs as a product. I want 2 NOs as a product. So it's on the correct side, but we just have too many. So remember, we can't subtract, we have to divide. So I'm also going to divide this one by 2. So if I divide the reaction by 2, I'm going to divide delta H by 2 also. But we're not going to flip this time. So 4NH3 becomes 2NH3. 5O2, 5 divided by 2 is of course 5 halves, or 2.5 O2. And then 4NO becomes 2NO. And 6H2O becomes 3H2O. So let's look at what our delta H's will be for this. Okay, so we're going to take our 1530 and divide it by 2. And remember, we changed it to positive because we flipped our reaction. So that's 765 kilojoules. And then for our second reaction, we did not flip. We just divided by 2. And so that becomes negative 585 kilojoules. Alright, so remember, things on opposite sides will cancel. So let's see what we have. Well, I have 3 waters here and 3 waters here. I have 2 NH3s here and 2 NH3s here. And the oxygen gets a little tricky. Remember, you can only cancel out as many as you have on both sides. So here I have 1.5, here I have 2.5. That means I can cancel out 1.5. So 2.5 minus 1.5, of course, is 1, so I'm just going to get rid of the coefficient. And so then I write what I have left. So I have N2 plus O2 yields 2NO. Is that the reaction I wanted? It sure is. So then I just added my delta H's. So delta H, of course, once I add these up, is 180 kilojoules. So hopefully you got that one right. Alright, so let's erase and move on. So up until now, we've only done 2 reaction ones. They can have as many reactions as somebody wants. Like they can have 2, 3, 4, 5. So this is a 3 reaction one. So again, just pause the video, try it, and then check your answer with me. Okay, so let's look at it. Alright, so what I notice is they all have oxygen, they all have water, and 2 of them have CO2. So I'm going to focus on these first things. Ooh, I'm going to have to write kind of small. I didn't leave myself much room down here. Alright, so I have 2 H2 as a reactant. I want 1 H2 as a reactant. So I'm going to divide this reaction by 2, which means I need to divide delta H by 2. So I'm going to divide by 2, so that becomes H2 plus 0.5 O2 yields H2O. And then, like I said, I'm going to divide my delta H by 2. And so when I divide that by 2, I get negative 286 kilojoules. Alright, so for our second one, I have 1 C2H4 as a reactant. I want 1 C2H4 as a reactant. So I'm not going to do anything to the second reaction. And so if I don't change the reaction, then I do not change my delta H. So it remains the same. So negative 1,401 kilojoules. Alright, so we left that one the same. So now look at my bottom one. I have 2 C2H6 as a reactant. I want 1 as a product. So this one I have to do 2 things to. I'm going to have to flip it to get it onto the other side. And because I only want 1, I'm going to need to divide by 2. So remember, that means I'm going to change the sign of delta H so it becomes positive. And I'm also going to divide it by 2. Alright, so I'll try to write as small as I can because I still need to add them. Alright, so I'm going to flip and divide by 2. So I'm going to start with this side first. So 6H2O becomes 3H2O. And 4CO2 becomes 2CO2. and then 2 C2H6 becomes C2H6, and 7 O2 becomes 7 halves, or 3.5 O2. And so then my delta H, of course, we changed to positive and divided it by 2, and so you get 1550 kilojoules. Alright, so this one, it gets a little messy because there's a lot going on, so just try to look through all my work. Alright, so let's look at something easy first. So let's look at CO2. So I have 2 CO2s, 2 CO2s, those go away. Let's look at water. I have 3 waters, and here I have 2 3 waters. Everybody see that? 2 and 1 is 3. So I can get rid of all of my waters. Alright, let's look at oxygen. So here I have 3 and 0.5. So that's 3.5 oxygens. Here I have 3.5 oxygens. So all my oxygens go away. And then I write what I have left. So I have a C2H4 plus an H2. So see, most of this stuff just canceled. Makes C2H6. Is that the reaction I want? It sure is. So then I add up those delta H's, and I got negative 137 kilojoules. Alright, so hopefully you think Hess's Law is pretty easy. It just takes a little bit of practice, but it's pretty easy. Like I said, I kind of feel like it's a game. You know, you can agree or disagree, it doesn't matter. I can't hear you if you disagree with me. Alright, so let's erase this and move on to the next type. And that's when I'll kind of pause the video, is in the middle of that, to make my part 2. Because otherwise this video is going to be so long. Alright, so the next type is standard heat of formation. So the standard heat of formation of a compound is the change in enthalpy that accompanies the formation of 1 mole of the compound from its elements with all substances in their standard states at 25 degrees Celsius. So what it's going to look like is delta H with a little sub F and a little degree sign. So delta H is, of course, change in enthalpy. The little F means formation, and the little degree sign means we're at standard state at 25 degrees Celsius. So the standard heat of formation of a free element in its standard state is 0. So like oxygen, O2, is naturally a gas. So the delta H of formation for oxygen gas is 0 because it just naturally exists that way. Now O2 is not normally a liquid. So if we have O2 as a liquid, it would actually have a delta H that's an actual value. So that's the important thing to know. A normal element in its natural state by itself is going to be 0. But it's got to be in its natural state. If you change the state, it's going to have an actual delta H. So where do you find these values? Well, in my class, you get the thermochemistry charts page. Okay, if you lose this, you can just Google standard heats of formation, and you can find charts with all of those numbers on there. Alright, so to calculate it for a reaction, you do your standard heat of formation of your products minus your standard heat of formation of reactants. Remember, change is final minus initial. Final is your products, initial is your reactants. Okay, so it's products minus reactants. So the way you'll see me write it in class is I'll just write delta H equals products minus reactants. That's just kind of a fast way that I like to write it. Okay, so let's look at one. I mean, we're going to look at more than one, obviously, but we'll start with one. So it says, calculate the standard heat of formation for the following reaction. Okay, so this is where our thermochemistry charts page comes into play, because I have to look up the numbers for each of these before I can do products minus reactants. Now when you look at a standard heat of formation chart, it will tell you the unit is kilojoules per mole. So you have to take into account your coefficients, because that tells you how many moles you have. Okay, so you've got to be real careful of that. The other thing you have to be careful of is your states of matter. Like if you look at this charts page, water gas is negative 241.8 kilojoules per mole. But water liquid is negative 285.8 kilojoules per mole. So the different states of matter have different numbers. Alright, so remember, your delta H is your products minus reactants. So let's just plug in. Alright, so here's my products. So I have a 2 here, so I'm going to say 2 times, and then I'm going to look up what CO2 gas is. So I'll look on my charts page, I find CO2 gas, and it says negative 393.5 kilojoules per mole. Okay, the reason I'm going to leave off the per mole is the reason I multiplied by 2 was there were 2 moles. So the moles are going to cancel. Alright, so I took care of my products. So now I'm going to subtract my reactants. So I have 2 CO. So I'm going to do 2 times. So I find CO gas. It's negative 110.5 kilojoules plus my O2 gas. Well, remember, O2 is naturally a gas. It's not going to be on here because it's 0 kilojoules. Alright, so close my parentheses. And see, that's the thing with all these parentheses and a bunch of them being negative. Some of y'all, your main problem is actually just putting it in the calculator correctly. Okay, like you can set it up all day long, but then you're leaving off parentheses or things like that and you have trouble putting it in. So once I solved this, I got negative 566 in kilojoules as my answer. Because remember, all the moles cancel when you multiply by the coefficients. I don't sit there and write all that out because it gets very long at that point. Alright, so that's what standard heat of formation looks like. So you just look up the numbers and do products minus reactants, and don't forget to multiply by your coefficients. That's the most common mistake that I see, is forgetting to multiply by those coefficients. So let's look at another one. Alright, so if you feel confident, go ahead and try this one on your own. If not, we can look at it together. So it says calculate standard heat of formation for the following reaction. Well, this one, notice, I don't have any coefficients. I don't have to remember to multiply by anything. So remember, my delta H is my products minus reactants. So I start with my products. So I have CaO solid. So I get my thermochemistry charts page out. CaO solid is negative 635.1 kilojoules. I don't have to multiply by anything because we're technically multiplying, we're technically multiplying it by 1. Alright, so then I'm going to add my CO2 gas. So I look on my charts page, I find CO2 gas, and it's negative 393.5 kilojoules. So there's my products. So now I'm going to subtract my reactants. So my reactant is CaCO3 solid, so I find that on my thermochemistry charts page, 1,207.0 kilojoules. And then I just solve. So like I said, the just solving is what you have to be the most careful of, is you have a lot of the negatives floating around and all those kind of things. It's real easy to make a little error. So I got 178.4 kilojoules for that one. Alright, so if you tried that on your own, hopefully you got it right. If you waited to see another one, then just try the next one on your own. Alright, so maybe pause the video, try this, and then check your answer with me. Alright, so we have delta H equals products minus reactants. So my product, I just have one this time, it's NO2 gas, but there's 2 of them. So I'm going to say 2 times, and then I find on my thermochemistry charts page, NO2 gas, which is 33.85 kilojoules. Alright, so that's my one product. So now I'm going to subtract my reactants. So I have NO, but there's 2 of them, so I'm going to do 2 times NO as a gas. So NO as a gas is 90.37 kilojoules. And then add my other one, which is O2 gas. That's its natural states with 0 kilojoules. And then I just solve. So when I solve, I got negative 113.07 kilojoules. So hopefully you got that one right. Alright, so we're going to stop the part 1 video here. Just again, I didn't want to make it so incredibly long and tedious. But next you'll be able to find the part 2 video because I'll have that one also.